Hey class, here is the video that covers section 6.3, and in order to do it, I'm just going to go through a little bit of the actual theory first, and you will see just how easy this section should be. And I will tell you this, the more you practice this section and the better you get at it, the easier it will be in the future. So here's what we got. It turns out that log base b of x equals y is absolutely equivalent to b to the y equals x. And most people just kind of just say, well, this is how it's defined. This is what it is. But here's the thing that you really need to pay attention to. All a logarithm is, and I can't stress this enough, all a logarithm is asking a question about what would the exponent need to be for something to be true. And here's what I mean by that. Notice over here, the exponent is y. And so if you were asking the question, b to what power is, well, let's say this. Let's say you want to know 3 to what power is 7. That's a hard problem. If you had 3 to what power is 7, I don't know the answer to it right off my head. If you had 3 to the x equaled 9, I could say 3 to the x equals 3 squared, and therefore x equals 2, and that would work out. But that only works when it's a power of 3 that I already know, such as 9 or 27 or 81 or something like that. The more important thing, though, is if you were asking 2 to what power equals 11, we are exactly in this situation right here, where b is 2 and x is 11. And what I don't know is, what is y over here? But look, y is that logarithm right there, and that is that power. So this log is nothing more than what power you would raise a number to get another number. So I said a logarithm is nothing more than asking a question about what would the exponent need to be for a certain situation to become true. And here's how I like to think about it. I see this little counterclockwise pattern in there. So I see b to the y equals x. And so b to the y is right there, and then equals x is right there. So bottom, up, and then around. Once you see that, watch how easy the first part of the homework is. So in this section it says, rewrite each equation in exponential form. Here's something I should tell you. This is called log form. This is called exponential form. And so notice all of these are given as logarithms, and it told us rewrite them in exponential form. So if I was going to do these, and I'm just going to write them over and make it kind of quick because I'm trying to illustrate a point here for you guys. I'm going to do all the evens in this. This would say 4 to the m equals q. So 4 to the m equals q. In problem 8, it would be 16 to the x equals y. In 10, it would be y to the negative 11 equals x. So y to that equals that. In 12, it would be y to the x equals 137. And 14, here is one of our first encounters, and we're going to do 15 also. There are two very special logarithms. And so if you just see log x and there's nothing down here, it's always understood to be 10. So just log by itself means log base 10. So that's one thing right there. So in this problem over here, it does not have a base down there, so the base is 10, and then it should be 10 to the t equals v. So 10 to the t equals v. And then over here, notice log ln. And so the only other one that you need to know about is ln. This actually stands for natural logarithm. And so it's an L and an N, and it's the way it's pronounced in the original language it was written in is something like logarithm natural, and so that's why it's an L first, then an N. Even though when we say natural log, I always thought too, then why don't we call it NL? That's not how it was first came up with. But when you see ln, that means log base e. And so where e is a very special number, e is approximately 2.7178288, and it goes on forever and ever and ever. Here's a few cool things I'll just tell you, because I can't not tell you this once we reach this point. E is what's called a transcendental number. And so is pi. And what that means is nothing more than that they can't be a solution of any polynomial with rational coefficients. And so if you just have fractions like a half x squared plus 7x minus 5, those are all rational numbers because they're all fractions. And so pi and e can't ever be a solution, meaning one of the roots where it crosses the x-axis. And then the other cool thing is pi and e are the only two transcendental numbers that we know of that are in popular mathematics. And it took a long time to know if pi plus e was also transcendental. But we do now know, and the answer is yes, it is. But it took, I think, 100 years or close to that to have that figured out. So e is a very special number. The letter e itself is, it comes from a very special mathematician named Leonard Euler. And so I know it looks like Euler, but it's pronounced Euler. And for Euler, that E is that E right there. And he's the only mathematician that I know of that has like a number named after them, so to speak. So that is very, very admirable, very respected. He was a very famous mathematician, one of the greatest mathematicians ever to live. So, anyway, the ln means log base e. And so, when you see something like this, we would have, there's an e down there, and it would be e to the n equals w. So, e to the n equals w. So there we've done 6, 8, 10, 12, and 14. All of the evens, you have the odds. And it's just that to that equals that. That to that equals that. E to that equals that. And so, anyway, these down here go the other way. And so, recall that log base b of x equals y is exactly the same as b to the y equals x. And so in these problems then, in 16, if you look, and I just kind of match this up, I go, okay, look here. I've got 4. 4 is where the b is, and the b goes down there. Okay, so then this should be log base 4. And then we come over here and I go, okay, y is the power, and so x is the power there, and x goes right there. Okay, so then that should be, hold on, I said it backwards because I'm switching the x's and the y's. So in this case, the y is the power. For me, the x is the power there, but since y is the power sits on that side, so I'm going to put x on that side, and then I see on the other side is x, but x for us is y, but x in the formula goes inside, and so I'm going to put y inside. Now here's the truth. Once you get decent at it, you can just see that, 4 to the x equals y. Oh yeah, that's what's written right there. So here is kind of that way of thinking even faster. So this should be log and an equals, and here's what I would do. I see it's m to the negative 7 equals n. And what I did in my head was said m to the negative 7 equals n. So I don't really, it's hard for me to go this way, but it's easy for me to go this way, if that makes sense. And not that I make mistakes on it, it's just, it's easier for me to see that to that equals that. And it's harder for me to see, that's the base of the log, even though that is the base of the exponential. And so that is the base, and so I do understand that. It's just not as fast a way for me to think. And so that's just how it is. In 20, I would say log equals, and then I see that it's x to the negative 10/13 equals y, and again, just to check it, x to that equals that. That's exactly what is written right there. And so I'm not going to do all of those, but you see the way that I think about it, and hopefully that makes sense. Down here, it's just sort of for you guys to have some fun. And notice it says solve for x by converting to exponential form. I didn't say this before too, and I thought about it partway through, but it was awkward. Notice all of these are given in exponential form, and it says to rewrite in log form. And so we want to take this and turn it into that. So that's why we were doing what we were doing there. In these problems, though, like take 26, for example, this says 3 to the 2 equals x. So 3 squared equals x. So 9 equals x. Notice it said solve for x. I have right there. In 28, it says 5 squared equals x. 5 squared equals x. So 25 is x. In 30, 2 to the 6th is x. So 64 is x, and so on and so forth. In these down here, it says use the definition of these to actually simplify. Now here's the 2 things that you need to know, also in addition to what I've already told you. So there are a few properties of logs, and you'll get into more of them as we progress. But there are 2 truths, and here is what they are. One of them is that b raised to the log base b of x equals x. And the second one is that log base b of b to the x equals x. And these 2 are known as the inverse function properties. And what I mean by that, I'm going to show you right now, and it's very cool. A function and its inverse are reflections across the line y equal x. And so if you have a function that looks like this, its inverse should look like that on the other side of it. I'm going to show you that right now by here. If I say, I'm going to say b to the x, add a slider for b, and then here I'm going to go functions and miscellaneous log, and I'm going to make the base b for x, whoops, for x, and this I'm going to change from 1 to 20, and we'll step by 1 each time, and maybe pull that up there. Okay, so here's what we have, you guys. As this starts, and then let's do this. Let's also put in y equals x. So I can't use the laser pointer in this program, but what I want you to see is that the red graph and the green graph look like they would lay perfectly on top of each other if I folded this as a piece of paper right along the purple line. So if I fold it along the purple line, it looks like the red graph will lay right on top of the green graph right there. And that works for any value I pick for b. Notice all it does is sort of change their natural trajectory in there. And so that shows that they are inverses to each other in a graphical form. So why is it true, though? It's true because, look, this says b to what power turns out to be x. And that power turns out to be log base b of x. And so if I took this and put it right there where the y is, that becomes this equation right here. Looking at it the other way, take this one to start with, and let's say I wanted to know log base b of what is y. Well, my what is right here, and my what turns out to be b to the y. So if I took the b to the y and put it right here, where that turns out to be, b to the y, notice you have a b and a b to the y, b, b, and an x. When it's b and a y, we get a y there. So if there's an x there, there should be an x there. These two properties do nothing more than just come out of this definition. And this definition for what a logarithm is, in terms of saying that it really is a question about a certain exponent for a base that makes something true. The way we've defined it, a logarithm is naturally the inverse to an exponential function. So that's kind of cool. But what that means then is, even more special, that 10 to the log x is x, and log of 10 to the x is x, because you don't need to write it down there. But it also means that e to the ln x is x, and ln of e to the x is x. So I will write those out of this. So what that means is 10 to the log x is x, or log of 10 to the x is x, or e to the ln x is x, or ln e to the x is x. And you could see all of that to be true if we went in here, because if I said 10 raised to the log x, notice that the blue and the black lay on top of each other. So that means that the black function does in fact equal x. If I instead did this and said log of 10 to the x, 10 to the x, notice that that stays and lays on top of it. If I said e to the ln of x, notice that lays on top of the line. And finally, if I said ln of e to the x, that shows that they lay on top of there also. One thing that you should notice and sort of expect is the following. If you've really read the section prior to this on exponential functions, since exponential functions only are positive, the range of this is 0 to infinity. The domain is negative infinity to infinity. What that means, and this is for a b to the x, it means when we take the logarithm, so this is log base b of x equals y. Since we know the range and the domain of this function, and this function is its inverse, what that means is the domain of this is 0 to infinity. And notice it only is defined from here over. And so there's nothing over here for that graph. This is the only place where it was. And you could see that by, if I said log base 2 of x, there it is right there. And it does stay like it's supposed to. And it never crosses though. There's nothing ever defined anywhere over here in the negatives, but forever in the positive, it's good. So you can go from 0 right there, from that 0 spot all the way to infinity in there. And so that's because the range of this function becomes the domain of its inverse. And the domain of this function, meaning you can start all the way down at negative infinity and go all the way to positive infinity. Not up here, but I'm saying the x's can keep going. That's what the domain is. Since it's the inverse, that means the range of this should be negative infinity to infinity. And you can see that because that goes forever down and that goes forever up, even though it looks like it keeps curving, and it kind of does in a sense. It just curves less and less and less and less and less forever. So it's hard to reason why it wouldn't eventually turn around and yet continually turn. That's for another day. So those properties are true. Those properties are called the inverse function properties. This is them for any base. This is specifically for base 10. And in base 10, we don't put the 10 there and we don't put the 10 there. And this is specifically for base e. And with e, we don't write log base e. Instead, we write ln. And we don't write log base e right there. But these rules with 10 and e are presented to you right there. And so, let's go back to the homework. Then look, this problem right here, what we would do is we would say, okay, well that's log, so it's log. But for the property to work, it has to be log of 10 to something. Well, I don't have log of 10 to something. I have log of 100. But 100 is 10 squared. So I can make that 10 squared to the 8th power. And now, how do you take an exponent to another exponent? You multiply the exponents. And so this then becomes log of 10 to the 16th power. Now, this property holds, so log 10 to the 16 should be 16. So what's the answer to this? It's 16. And you can see that would be the answer if I did this and said, what is log of 100 second raised to the 8th power. There it is on the right hand side over there. I can't point to it with the laser pointer, but you see that it is 16. And so that is how you get something like that. If you had something like 38, here's the deal with 38. So one thing I'm going to do is just clear the page here for a second, and watch this. So this is 2 log, and what I'm going to do is this. That's tenths, hundredths, thousandths, 10,000ths. So that's 1/10,000th. But that's 2 log, and 1/10,000th is 10 to the negative 4. You could also say, if we put here, it would be 1, 2, 3, 4 to get there. So since we're going left, it is 1 times 10 to the negative 4th power. And then now that I have log 10 to the negative 4, it should be negative 4. So this part right here is negative 4. And what's 2 times negative 4? It's negative 8. So if we checked in a calculator, if I did 2 times log 0.0001, the answer is negative 8. And so that's how you think about the problems in this section. Same thing with the e's and the ln's. They will just wipe each other out. The answer is negative 5.03, and so on and so forth. Down here, it says evaluate them without using a calculator. And so the cool thing about this is if I took problem 42, if I did this, I would say, okay, well, I don't know what it is right now. So to evaluate it means, what does that thing equal? I do know it's negative 3, but right now, let's say I don't know. And if you're wondering, how did I know that so quick? I told you in the beginning that a logarithm, and remember, very specifically, that's not there. So a logarithm is, and I told you over here, a logarithm is nothing more than asking about what power would something have to be. So what I say is 3 to what power is 1/27th. But what I know about 1/27th very quickly is it's 3 to the negative 3rd. Let's see how this works though. So I'm going to show you 2 ways to do this problem right here. Let's take it over here. So they gave us log base 3 of 1/27th. So one way of doing it would be using properties. And what I mean by that is the following. You could say, well, that's log base 3 of 1 over 3 cubed. 3 cubed is 27. And then that really is log base 3 of 3 to the negative 3. And in, over here, log base 3 of 3 to the negative 3. If x is negative 3, the answer is negative 3. So over here, it's almost as if the log base 3 and the 3 base wipe each other out, and all that remains is negative 3. So the answer is negative. That's one way of doing it. The second way of doing it would be to build an equation. And what I mean by an equation is this. I would say, well, log base 3 of 1/27th, I don't know what it is right now, so let's call it x. Then using my property, I would say that to that equals that. And so I can say 3 then to the x equals 1/27th. Then I could say 3 to the x is 1 over 3 cubed, or 3 to the x equals 3 to the negative 3. And since the base is the same, the only way you can have a base to two different powers seem to be equal is only if the powers are equal. So that only happens if x is negative 3. And notice, that's what we got over there. And so I would still in this have to come back and take the x away and say, okay, so then it equals negative 3. But in the beginning, there was an x right there. And so that's kind of my way of understanding it. Then just sort of flipping through here. This is, well, it's 4, I'll tell you right there. How do I know that? Because it's a 10 base, and 10,000 is 10 to the 4th power. So since it's a log of 10 to the 4th, those wipe, and the answer's 4. Log of 1, log anything of 1 is 0, and you will come to learn that. But the way that you know that is right here. At 1, it's 0. So log 2 of 1 is 0. But more importantly, if I changed it to be log base b, whoops. Let's do this. All right, let's do log base b of x. Whoops. Of x. So as we move this, all the higher and higher base does is just make it a little bit flatter. And so this is a lot more curved down here, a little flatter down there. The thing to notice is the entire time, no matter what, it stays through the point 0, 1. Or 1, 0, sorry. 1, 0. And then there, as I change, you can see it doesn't ever change. So what that means is, since the x value is 1, that means log base b of 1 is just 0. You see that for any base. And why is that true? That is true because when I say log base b of 1 equals 0, for every b, so for every b greater than 0 not equal to 1, because what is true? B to the 0 is 1. Haven't you your whole life been told anything to the 0 power is 1? Anything not 0 to the 0 power is 1. 0 to the 0 is a different story. But b to the 0 is 1. And so that means log base b of 1 is always 0. So down here, That's 0. So that answer is just 7. And so any of these mess around with the E. So that's E. And since that's an E and an E there, they wipe each other out. That answer is 1/3. This one is whatever negative 0.225 minus 3 is, because those would wipe each other out. And so that's how you do the problems in this section. They are all fairly simple. Don't make them more than they need to be. Please remember that all a logarithm is nothing more than asking, if it really is y, it's asking what power would you raise b to in order to get x. And so it is very, very useful. And not so much if you're asking 2 to what power is 8, because we know 2 cubed is 8. But 2 to what power is 7? That's a whole different story. And so, but logarithms come to our rescue and save the day. Anyway, good luck with this, you guys. Take care. And I am proud of you. All right, hang in there.